Okay, so today's lesson is going to be on the collision theory, and the collision theory is a theory that helps to explain why chemical reactions occur and how they are able to happen. The collision theory states that a reaction occurs when two things have to happen. Two or more particles must collide, and they must collide in the correct orientation, but they also must collide with enough kinetic energy to overcome activation energy. All right, activation energy being the amount of energy needed to get a reaction started. All right, if not enough kinetic energy, then there's going to be no reaction. If we are not colliding in the correct orientation, again, no reaction. So both things must happen. We have to have enough kinetic energy to overcome activation energy and the correct orientation. So let's look at this equation. Carbon monoxide gas plus oxygen gas yields carbon dioxide gas. And I've drawn it in terms of a particle diagram, all right, where my carbon is the solid and my oxygen is the unshaded. So, if I have a carbon monoxide and an oxygen, let's look right here. Carbon dioxide has a carbon in the center with an oxygen on each side. So if oxygen from the carbon monoxide collides with an oxygen from the oxygen gas, there is no reaction. This carbon dioxide is not a carbon with two oxygens. It is a carbon with oxygen on both sides. So then in order for this to happen, the oxygen gas actually has to collide with the carbon side in order for an oxygen to combine over to form carbon dioxide. The more collisions there are, the faster the reaction occurs because there's a higher statistical probability of those collisions having enough energy to overcome activation energy and in the correct orientation, right? The more collisions, the more likely we are to have a reaction. So let's look at some things that will affect our reaction rates. Temperature. If I increase temperature, remember temperature is the measure of the average kinetic energy. So if I increase temperature, then I increase kinetic energy. If I'm increasing kinetic energy, those particles are more likely to collide with enough energy to overcome activation. If I decrease temperature, then I have less kinetic energy. If there's less kinetic energy, they're less likely to collide with enough energy to overcome that activation. So we decrease the rate. Concentration. If I increase the concentration, I increase the number of particles. If I increase the number of particles, I increase the number of collisions. More collisions, higher reaction rate because they're more likely to collide with the two things in mind that we've discussed that are needed. If I decrease the concentration, I decrease the reaction rate because I'm decreasing the number of particles. Less particles, less collisions. Surface area. If I increase the surface area, then what I'm doing is I'm increasing the collisions and the orientation is more likely to be correct, and therefore a higher reaction rate. When I dissolve a solid, then what that does is it allows us to increase the reaction rate because energy is no longer needed to break the solid apart. That solid is already in its ion form. So by having ions instead of a solid where I have to first have energy to break the solid and then energy to overcome activation energy, now all I have to do is have a collision with enough energy to overcome activation energy. So we are actually increasing the rate by dissolving. If I decrease surface area, then I also decrease the reaction rate because those collisions are less area, less space for those collisions to occur. pressure. If I increase pressure, then we know that's going to cause an increase in collisions. More collisions, higher reaction rate. If I decrease pressure, then I have less collisions. Decrease in pressure, decrease in number of collisions, a smaller reaction rate. Catalyst. Catalysts are going to work by lowering the activation energy, which we write as E sub A. All right, so if I need less energy to get that reaction started, then my collision, when it collides, is more likely to have enough energy for that reaction to occur. Because if I need less, then that's going to help to increase the reaction rate. Now, we know that catalysts are reusable. All right, they are used over and over again. And we're going to look at catalysts more in depth when you come see me in AP Chemistry. And we'll actually talk about a little bit more about how the catalyst actually works and how it is reusable. All right, let's look at our structure. And in this structure example, I have carbon dioxide and ammonia, and I've drawn the Lewis structures for both of these. What do we notice? Carbon dioxide has double bonds. Ammonia has single bonds. We know that single bonds require less energy to break than a double bond. Now, what's happening in a reaction? Reactants, the bonds of the reactants are being broken apart and reformed in the product side. So energy is required to break these bonds. All right, so because it's going to take more energy to break a double bond, carbon dioxide is going to require more kinetic energy than the ammonia. Okay, so it's more difficult to break those bonds. So the reaction rate for carbon dioxide, we would expect to be slower than that for ammonia, given the same conditions, same temperature, same concentration, same pressure, same everything. If we held everything constant and looked at these in terms of just the structure, we would see that carbon dioxide does in fact require more energy to break.